Hi, my name is Sean Perry. Welcome back to a lecture series on Calculus 3. This will be the fourth video in the series, and we're going to be talking about some important operations and functions in R3, the space of three-dimensional vectors. So this will be, I anticipate, a bit longer of a video. So for those of you who don't have the time, here's the TLDR. We're going to talk about the natural orthonormal basis of R3, that is the coordinate vectors I, j, and k, and how to take any vector u and write them as a linear combination of I, j, and k straight from the coordinates that defined u. So pretty natural thing to do. We're then going to talk about the dot product, just like in R2, or the vectors in the plane. The dot product is going to be defined as the product of the coordinates summed. We can also, in the exact same way, describe it as the product of their two magnitudes times the cosine of the angle between them. Now, however, the cosine of the angle between them needs some clarification because we're in three dimensions. So any two vectors are going to determine a plane, and it's in that plane that theta, the angle between them, is going to be measured. We didn't talk about this in the last video, but I meant to. You can also, if you're given the dot product and their magnitudes, find the angle between them, up to a sine and multiples of 2 pi, of course, but just using inverse cosine, basically solving the formula with the dot product and cosine of theta for theta. We're then going to talk about a new product, which we didn't talk about before, called the cross product. This is a bit more tricky to define. It's actually, instead of giving us a number, like the dot product does, it's going to give us a vector. And that vector is going to be normal or orthogonal to the plane that has the vectors u and v in it. There's a few different ways to remember what that formula is. We'll go over that. But it also has to do in the same way dot product has to do with cosine. This will have to do with sine. But now we'll be multiplying by this unit vector, which is normal to the plane. The last thing we'll talk about is the scalar triple product. We'll talk about that briefly. That has to do with volumes, calculating the volume of this shape, the parallelepiped, that is spanned by u, v, and w. So that also has a similar formula that you can express in terms of determinants. We'll talk about those. And that'll probably be where we stop. So, to begin with, we can define, the same way that we did before, an orthonormal basis for our vector space. It's ortho because these vectors will be at 90 degrees to one another. It's normal in the sense that it has norm 1, or these are all unit vectors of length 1. And it's a basis because we could take any vector and express it this way. So just to draw the picture again real quick, if I have a coordinate system, and I have some u in that coordinate system, so any vector, and let's say this vector has components x, y, and z. Then we can take and decompose this in terms of a sum of, or a linear combination of basis vectors. So perhaps along the x-axis, we might have the basis vector I. Along the y-axis, we might have the basis vector j. And along z, we have k hat, right? We call this the hat symbol, and it denotes that these are unit vectors having length of 1. So if I want to, as it will be frequently better to write things in terms of these basis vectors than in terms of coordinates, we can write u the following way. Right? We just turn these coordinates in component form here into the scalars that multiply these basis vectors when we do a linear combination. So in other words, this will be x times I hat. Plus, well, try to keep things color-coded like I have in the notes, but you know, if I find this is wasting too much time, maybe I will go back to monochromatic. Y, j hat, and z, a number here, but merely meaning the axis here. That's why I've color-coded them differently. Times k hat. Sorry for the abuse of notation with x, y, and z, but you'll find we run out of symbols pretty quickly in Calculus 3, and so there's going to be a bit of abuse, meaning two meanings for one symbol. I will try to use color coding to distinguish when I mean two different things. So let's do an example to try to get an understanding of how this works. So let's define a vector PQ using the initial and terminal point version of a vector, right? So we say it has initial point P equal to the coordinate, notice the parentheses, not the angular brackets. Let's say 3, 5, or 3, 7, and negative 5. Let's say it has a final point Q that's at -3, 10, and 2. And let's write it in its various forms. Let's write it in component form first. So in this case, PQ would be equal to, well, we just take the difference of the two components again, final minus initial. And this will be it in component form. So let's just evaluate that quickly. That's -6, 3, and 7. So we would have a vector pointing this way. 6 units in the x direction, 3 units in the y direction, and 7 units up. Now, if we wanted to write this in basis vector form, we could. We just take these components and we multiply by the basis vectors I hat, j hat, k hat. And then we sum them. Or this is now, by the definition of how we sum two vectors, tip to tail addition. And finally, just as a quick review, let's say we wanted to know the norm of PQ. So we distinguish that this way. This is its magnitude. And how do we find magnitudes in R3? Well, the exact same way that we found them in R2. We use the Pythagorean theorem. But as some of you might know, if you've ever calculated the diagonal distance across a box, the Pythagorean theorem in 3 dimensions looks an awful lot like it does in 2. It's the square root, the hypotenuse is the square root of the sum of the squares of the sides. So, for example, we're going to want the square root here of the length of each side squared, or just take it squared, because I mean, you're going to square it, it's going to become positive, doesn't matter if it's negative here, plus 3 squared plus 7 squared, and if we work that all out, this is the square root of 94. Okay. So next, we are going to take a look at the dot product. So the dot product is described the same way as it was before, in the sense that we're going to be looking at a sum of the products of the components. So let's define U as x1, y1, z1. And here I could say, xu, yu, zu, but it gets harder to distinguish u from v when we are looking at subscripts. It's very tiny down there. And so rather than say that, I'm just going to associate u with 1. Okay? And then our v vector will be x2, y2, z2. And the definition of our dot product is going to go as follows. So let's take u dotted with v. So I'll use red for my operation here. Okay. And that's going to be equal to the sum of the product of each component, sort of pairwise, right? We're going to take our x's together. So x1 times x2. And then we sum them. So then y1 times y2 added to z1 times z2, and we're done here. So the main idea is that you can see how this is a generalization from the R2 definition. And in fact, the dot product easily extends to n dimensions, right? You could take an n-dimensional dot product, you just do the same thing. You just multiply the components together and sum them. And we have an additional interpretation here when we're talking about these, vectors in our Euclidean coordinate space. We can also say that this is going to be the magnitude of u times the magnitude of v times the cosine of the angle between them. And as I mentioned in the intro, we now are talking about an angle inside of the plane that they both span. Let's think about when that is the case. Now, obviously, if they are 0, one of the two or both is 0, then this whole sum is 0, right? And they don't span a plane at all. They don't make any kind of a plane. It's either just the line still or 0 itself. However, if they are, let's say, both non-zero, if we have u and v are parallel, so I'll just write this monochromatically. If u and v are parallel, well, that looks like the Absval symbol. I'll just write parallel. Then you have theta, the angle between them is equal to 0, or at the very least coterminal with 0. If you're counting multiple wrappings as still being parallel, we'd say coterminal for the angle, but equal to 0, fine. Right, and then that's going to be, then they lie on a single ray, right? If you had u and v both kind of going in the same direction. On the other hand, if you had u and v anti-parallel, then theta would be coterminal with 180 degrees, and you'd have something like one pointing in one direction and the other pointing in the other direction. Okay, so in one case they sort of span a ray, but linear combinations of them would still span a line, and in this case, same thing. They both kind of lie on this one-dimensional kind of an object. They both lie on a line. On the other hand, if they're neither, if they are neither, then they even if we're in 3 dimensions here, if they don't lie on the same line, then they kind of sweep out an entire plane, right? Let me actually try to draw this a little bit better. So let's get some axes up here. And let's say here is my v, and here is my u. Then if you sort of fold one to the other in your mind, you can see that they occupy a plane. I'm going to make it kind of part of the homework today to prove that they determine a plane. But it is in this plane, right? The main idea here is that this would be the plane, the one they both lie in. That's where we're going to measure theta. So there really isn't like a difference between this theta and theta's angles that we've looked at before, right? We're still measuring it in a plane of sorts. Okay, and so then we also kind of want to talk about some of the properties that we had in R2. Do they all kind of carry over nicely into R3? And for the most part, yes. The dot product is a pretty nice operator. It still gives us a number, right? It still takes in 2 vectors and spits out 1 number. And we have, for example, the following nice properties. For any vector, if you were to dot product it with itself, well, just think about it. You'd get the sum of the components squared. That's almost the Pythagorean theorem. In fact, if we just write the magnitude squared is equal to the dot product, this is literally the Pythagorean theorem. It's a pretty general way of writing the Pythagorean theorem in any number of dimensions. You can keep in mind 3 dimensions for this video. That's the one where we're going to be doing most of our business. Additionally, we have commutativity. And that should be clear because all of the operators used to define it are commutative, right? Multiplication's commutative, addition's commutative. So if I do a bunch of addition and multiplication, that should still be commutative. Okay. And then we also have that their dot product will be equal to 0, if and only if they are orthogonal. That is to say, if they are perpendicular to one another. And we'll count the 0 vector as being perpendicular to everything for this because the 0 vector is always 0, gives you 0 when you dot product it with anything. But, technically, if we think about physical orthogonality, maybe that doesn't make as much sense. But, formally, we'll say it's orthogonal to every vector. So that this is easier to state. But you could just think, oh, well, what if they're non-zero? Okay, right? Well, if I have a non-zero product equal to 0, they are at right angles to one another. What else carries over? Projection. Projection carries over. Remember, projection we could define using the dot product. So I'll try to just give a brief sense of what that would look like. Recall from the last video, projection is sort of like casting a shadow on the other vector. Right? Maybe I have u, maybe I have v, and maybe if we, in that plane, shone a light straight down, right onto v, something like this, right? Well, then we're going to get another vector, and that, so I'll put this over here, just color-coded. That is the vector projection onto v of u. And it's still defined the exact same way as it was before, where you have the dot product, and we divide by the magnitude of v squared and multiply by v. Another nice way to see this, well, actually that's getting into some review. I'll let you consult the video immediately previous to this one if you want to see why the projection has this formula. You know, once we're talking about being in a plane, we could just look at R2 anyway. So check out that video if you want to know more about this formula. Its magnitude alone, right? Its magnitude alone, the magnitude of the projection vector, is still going to be the scalar product. Well, is still going to be, excuse me, is still going to be what we call comp, or the component along v of u. And that, because if you think about taking one of these magnitudes and bringing it over to v, v divided by its magnitude is a normal vector. That just has length 1. That's a unit vector. So that doesn't change anything about the length of this. So its length is merely going to be u dot v over the magnitude of v. Likewise, unit vectors also work exactly the same way in R3. If I have a sphere instead, right, and that sphere has, you know, 1 for its radius, then your vector u, I have here like a vector u coming out, let's say it intersects the sphere at a certain point, right? And then the vector of that length, we'll call u hat, has length 1. It is a quote-unquote unit vector because it has length 1. And we can define the unit vector from the other vector. All we have to do is divide or scale, right, the unit vector by its length. Remember when I say u divided by its magnitude, right? You can't divide or multiply vectors quite yet. I mean, not in the same way that we can with numbers. So what does this mean to divide it by a number? Well, it's just multiplying by its reciprocal, right? You are scalar multiplying by 1 over the length of the vector against u. That's what that means. So this will allow you to take any vector, even if it's smaller than length 1. Even if you started with something smaller here, then dividing by its reciprocal would extend it, scale it up, and you'd get a vector of length 1 when you were done. So I'd like to say a little bit more about theta. Right, let's say that if we know the dot product, right, recall if we have the dot product u dotted with v, then this is going to be magnitude of u times the magnitude of v times the cosine of theta, the angle between them. But likewise, we also had another way of calculating the dot product as the sum of the components multiplied. So perhaps we already have this one. Maybe we have this in component form, and there's no reason to know theta. Well, look, that would make theta the only thing you didn't know. Oh, so we could solve for it. If we knew what the dot product was and we knew what each of the magnitudes was, which we definitely do if we're given it in component form, then we can solve for theta, right? Then, for example, cosine theta is equal to, get over there, oh dear, cosine theta is equal to the dot product, whatever that is, whatever number that is, divided by their magnitudes. And in the same way that we would solve a trig problem for this, we could solve for theta, or at least up to multiples of 2 pi and up to sine, because cosine is even, right? So that means cosine of theta and cosine of negative theta give you the same thing. So how could you ever discern between theta and negative theta if all you knew was cosine? You don't. You can't. So we can only get this up to a certain degree. I'll talk to I'll say a little bit more about solving inverse cosine instead of just telling you to review your trig like I did last time, which was maybe a little cavalier. But the point is that there is a method to do this. So in principle, we can get the angle between them if we know a little bit more about the vectors at play. So before I actually do the example, let me talk a little bit about what I just said, right? Like if you know cosine, right, what does cosine look like? It starts at 1, dips down, comes back up, right? Where does it do these things? Well, it repeats at 2 pi or 360 degrees. It goes all the way down here at 180. And notice that the y values will repeat outside of this window from 0 degrees to 180 degrees, or to pi, whatever you like, radians, what. So in a certain sense, if I want to give you a y value and say, hey, here's your y value, here's your value of cosine, then what is the value of theta that gives you that? You're never going to get one answer. I mean, first of all, cosine repeats over here too, right? So if we just ask this question sort of naively, because it fails the horizontal line test, its inverse function is not a function at all. It's a multivalued map. It tells you all of these things if you asked for the full answer. So what does inverse cosine do, for example, if you type it into the calculator? Well, it restricts you. It says, well, I'm only going to tell you the answer back inside of this interval, because that's where it does pass the horizontal line test. So it'll seek out just this answer and return that value for you. That'll be what you would get if you typed in cosine of inverse cosine of something into your calculator. But of course, if that was true, because cosine is even, minus that would also be true, right? If you had some value here that worked, then minus that would also work. And if you went up by 2 pi from that, you'd get another value that worked. Or up by 360 degrees, you'd get another value that worked. So, are there really an infinite number of angles such that cosine of theta is equal to some particular value? Yes, of course. But if you're only interested in one that's between 0 and 180, then you can get one answer back. And maybe that's all we should be concerned with, right? If I have something that's bigger than 180, right, I could instead measure it on the other side, and then I'd get something between 0 and 180. Likewise, if I imagined that this way was positive, right, but I wind backwards so that technically my angle is negative, all right, well, yeah, but we could also imagine starting at the other angle and winding forward so that the angle between them was positive. So maybe we should just content ourselves with only getting an answer back between 0 and 180. Let's look at an example. Oh, yeah. So here, let's pick some real or some tangible vectors. Let's say I have u given as 3, 2, 1. And let's take v equal to 1, 2, 3. Are these orthogonal to each other? Well, we'll see that they're not. But for right now, at the very least, we see that they're not scalar multiples of each other, right? And that's really all we need to determine a plane. If you have a vector, right, the only way that you are along the same line as that vector is if this is some constant multiple times your vector, right? Even if you're going in the other direction, right? You'd still just have a constant multiple. If it's not equal to a constant multiple, well, then you are not going to be parallel. They might be orthogonal, but they're not going to be parallel, so they're going to span a plane. We're going to be able to measure an angle in it. Where was I? Oh, right. So calculating the dot product of these two is not too tricky, right? If I say, what is u dot v? Well, then this is 3 times 1 plus 2 times 2 plus 1 times 3. And what do we get? 1 or 3 plus 3 is 6 plus 4 is 10. And then what about my magnitudes? Well, the magnitude of u, right, is the square root of 3 squared plus 2 squared plus 1 squared. That's 9 plus 1 plus 4, that's 14. And it's not too much effort to see that, you know, the absolute value or the magnitude of v is the same, right? Because that's 1 squared plus 2 squared plus 3, so it's just the other way around, right? I picked those just to simplify things a little bit. Okay, so then what do we have? Well, we know what cosine of theta is going to be, right? It's going to be their dot product divided by their magnitudes product. Okay. So that's going to be 10 divided by the square root of 14 times the square root of 14. In other words, 10 over 14. So that's 5 over 7. And from there, we could say that, you know, theta was equal to, or up to a sine and multiples of 2 pi, it is equal to the inverse cosine of 5/7. And that's a thing you could type into your calculator and get, you know, a decimal back, right? If we want it in degrees, shall we say that's 44.415 and so on degrees. All right, moving right along, let's talk about the next kind of product between two vectors, R3, which is going to be the cross product. Now, the cross product is going to be very different than the dot product. The cross product is going to take in two vectors and give you another vector instead of giving you a number like the dot product does. So let's start again with, you know, some component version of u. I'll call this x1, y1, z1. Again, if you're following along at home and you want to call this ABC, or you want to call this XU, YU, ZU, or UX, UY, UZ, I'm sure. Whatever, you know, what's in a name. A rose by any other name would still be the same components for these vectors. But these are the ones I'm going to use. Okay, so those would be our 6 numbers and defining our 2 vectors. And now, what is the cross product? So we write U cross V. And, you know, this is going to give us another vector in our R3. So let's write it in component form first. That means, having 3 spaces here. The formula's a little long, so I'm going to try to space this out right first. And I'll try to talk about what makes the formula pattern in just a moment. But suffice it to say, in the x component, the first component, we're only going to use y's and z's. It's everything else, right? And it's got to do with a product and a difference. We're going to take the product of the diagonal here, y1 times z2. And we're going to take the difference of that and the other product. So the difference between that and z1 times y2. Then we're going to do the same thing here. We're just going to move everything 1 down. So by going 1 down, we're going to be starting, instead of at y, we're starting at z. And now we're going to have to go sort of back to where we started from. Like you were playing Asteroids or some video game and you went off the edge of the map and came right back on the other side. We're going to go z down to x2, right? So this is going to be z2 times, or sorry, z1. I'll try to keep black coordination on all of the ones, all the ones that have to do, coordinates that have to do with u, z1 times x2 minus, and now we do the other diagonal, which is going to be, if we're doing y's, then we're doing x's and z's, right? We're omitting y, and we're going to do x1 times z2. And now we're sort of shifted over again. So now we're talking about x's and y's, and now we can see the cross again more easily. We're going to be doing x1 times y2 minus y1 times x2. And you might be thinking to yourself now, why on earth do we care about such a formula? And I'll try to provide some geometric reason for that. In the same way that you might have said, why do we care about the product of these two lists? And then it turned out that there were lots of great geometric reasons why you should care about that product. The same thing is going to happen with our cross product, where this seems arbitrary right now, but eventually you're going to see that it has some really interesting geometric significance. But before we move on to that, let's just write it in basis vector form. And I'm going to write it a little bit differently than these coordinates because I want this to line up with another way that we're going to write the formula later. That is with the sort of determinant mnemonic for the cross product. So, but, let me write these basis vectors. And part of that mnemonic involves factoring out a minus sign here, but not here. And as we discuss the determinant, you'll see not maybe why that minus sign exists. I'll leave it to your linear algebra class, or if I do a linear algebra video series, we'll worry about that then. For right now, that one stays the same. This one's going to get factored out, and so now I'm going to have the x1 term is first, and our x2, 2, and we're taking their difference. And this one stays the same. So this one's going to be x1, y1. We take the product of that against y2, x2, and we take their difference. Okay, so to get right into a bit more about the geometric considerations of the cross product, let's write another formula very similar to the formula that we had with the dot product involving an angle and a cosine of that angle and magnitudes of the vectors at play. There's also a very similar looking one for the cross product. It turns out this is going to give us magnitude of u times the magnitude of v, how long they are, times the sine of the angle between them. Well, not exactly. I mean, this is in fact the magnitude only of u cross v. Right? Because that's just a number. And we know from, this notation, but also, because I said so, that these cross products give you a vector. But this is the magnitude of that vector. You need two things to know what a vector is entirely. You need to know its magnitude, and you need to know its direction. Where is it pointed? And here we have half of that. We have the magnitude of the cross product, and it's given by sine of the angle between them times their magnitudes. Now, should you believe me? Of course not. Trust no guru. Trust no expert. Verify, right? Verify. A true guru, a true expert should be able to explain it to you. And I'd like to take a brief moment and prove this relation. So I have it written here. Let's go through it. It's not a long proof, and it's got a portion that I want you to do at home, as all good proofs should, infuriatingly enough. But isn't that the substance of it? I mean, that's why you shouldn't trust the guru, why you shouldn't trust the expert, because you should be doing some of this thinking. The onus is on you, right? The responsibility is on you, the thinker. Use that brain, especially when it's just like a quick algebra step, right? That's why you learn all this algebra, is to verify that I'm not just BSing you up here. Okay, all right, enough philosophy. So let's write magnitude of u times the sine, times the magnitude of v times the sine of the angle between them. And let's use a trigonometric identity to make sine into cosine. Why cosine? Because then we can leverage the dot product and all its formulas against this new definition, right? So what would we have then? I'm not going to change u and v right now. Leave these guys right here. But I am going to look at sine. And specifically, remember the Pythagorean identity. You know that sine squared of theta plus cosine squared of theta is equal to 1. In other words, solving, sine of theta is 1 minus cosine squared of theta square rooted. Okay? And let me drop this equal sign a little skewed because this is going to get longer. But what do we know about cosine squared? Well, I erased it, but we know the dot product formula, right? So leaving these two guys again the same. Then I have what? 1 minus. Now, cosine was the dot product divided by the magnitudes, and now we're squaring that. So let's get a dot product up here. Let's divide by the magnitudes. But we're going to be squaring all of these things because I'm squaring cosine here. Let me write that. And we're going to have v, and its magnitude. And we're going to have u, and its magnitude. And that's just, what we proved in the last video as being the relationship between the dot product, the sum of the products of the coordinates, and the angle theta. Okay? Now, one more step here. Let's bring something inside of this square root. Remember, you can always bring something inside of a square root. If I have some constant times a square root of blah, 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 then I can bring this inside as the square root of c squared times blah, 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 right? That's just square roots, baby. So let's bring this guy inside. And we have then magnitude of u squared times the magnitude of v squared. And this would be distributed against both of these if we were going to, be taking the product of what's inside. Product of this, but distribute it to the one, you get this. And distribute it to the other term. And, oh, hey, they cancel. Oh, that's nice, right? Right, we have this times 1 over that. We have the squares times over the squares. So all we have left here is the dot product squared. Okay, so now the dot product, we have a alternative formula for. And likewise, we have an alternative formula for these magnitudes, or rather we have the Pythagorean formula for finding the magnitudes. And these are the magnitudes squared, which is great, no square roots. Now we're just talking about a sum of squares. So what do we got? Well, this is going to be x1 squared plus y1 squared plus z1 squared times x2 squared plus y2 squared plus z2 squared minus, and now we're going to take the product of, so maybe I need some, oh no, we're going to take the dot product of these two things, right? So I have a formula for that, of course, right? That's just going to be the product of their components. So we'll have x1 times x2 plus y1 times y2 plus c1 times z2, and that's our dot product. Okay, so here's the part you can check at home. I want you to FOIL, or expand, I should say, all of these things, all 9 of these products, and then subtract the middle terms. And what you're going to find is you have this big old crappy list of things. Okay, well, I want you to check then and see if you could factor that big crappy list of things as follows. If you just want to check it, try expanding what I'm going to write and see if you get that big crappy list of things. But if you do, and if you do it right, what you're going to get is as follows. Oh, sorry, Z2. And that will be then Z1, Y1, But it won't just be that, because this is why you're going to have to factor these things. It'll be squared. Plus, and I think you probably see where this is going, d1 x2 minus x1 z2 squared plus x1 y2 minus, oops, I forgot my 1, y1 x2 squared. So when all the dust settles, we get it. And what is the square root of the square of these things? Well, these are the components of u cross v. So the square root of the sum of those squares is the magnitude of u cross v. QED. Okay, moving on. So this is going to be an important formula, an important way to interpret what exactly the cross product is. Another thing that we would want to know is what direction does it point in, right? I mean, now we have its magnitude. It's in terms of the angle between them and their magnitudes and the sine of the angle between them. Yes, yes. But what direction does it point in? I mean, that's the next thing to figure out. So here's what I can tell you. You remember the plane that u and v span, right? It's orthogonal to that. How do we know? Well, what we can show is that u cross v is orthogonal to both u and v. And that's enough to show that it's actually orthogonal to every linear combination of u and v, because you could distribute the dot product. Let me show you what I mean by that. Right, so right, this is true because u dotted with u cross v is 0, as is v dotted with u cross v. And because of the linearity of the dot product, if I had u cross v and I dotted that with any linear combination of u and v, which is the whole, this is everything in the plane of u and v looks like this somehow, then what I would get by the properties of the dot product is a times u cross v dotted with u plus b times u cross v dotted with v. But we just said both of those are 0, so that's 0. Right? This one is 0, and this one is 0. So it doesn't matter what a and b are, both of these things get sent to 0. And by the way, the proof of that is literally just carrying out the components. I have those in the notes. You can find those in the Google Drive link in the video description. But you really also could check that for yourself, because if you just write down what this is in terms of the coordinates and you dot it with u, you write down what that is in the terms of the coordinates, you will see that the sum is 0, right? You'll have cancellation, beautiful cancellation of terms, and that'll be that. Okay, so that tells me something. That tells me if I have V, right, and I have U, U, the vector, V, the vector, and these are in some plane. So I'll try to draw that or just suggest that like this. Here's a plane, right? And they're both lying in this plane. Then where does n go, or where is the cross product directed? Well, it's either this way, or, well, there's another option. Is it this way? Right? Is that u cross v? Both of those, both of those would be orthogonal to the plane, right? And we actually already have an answer for that, right? We can look back on the coordinates and determine what side of the plane this should go in. But for right now, I'm going to just kind of show you how this goes with the right-hand rule. It's not this one. So let's talk about the right-hand rule. Our hands are not symmetric with one another, right? I have to either face them back to you and then the thumbs point in different directions, or I have to face them forward and then the fingers bend in different directions, right, in order for the thumbs to point in the same way. We call this chiral. You'll hear that in chemistry more often, but you know, mathematicians would say they have a different orientation to them, right? There's something different about my left and right hand. So the right hand is going to be the one that we use to determine the orientation of the cross product. And that actually derives directly from how we picked the coordinate axis. If you'll remember that first or second video, we talked about how if x goes this way and y goes this way, right, then z has to point up my thumb's direction in order to give me a right-handed coordinate system. And that same rule is actually going to give us the correct orientation, direction of the cross product, right? If your index finger points in U's direction, and then V points in your middle finger's direction, or you curl your fingers towards V, then the thumb points in the direction of the cross product. So in this case, U this way, V that way into the page, so to speak, would give me a U cross V going up in the thumb's direction. U, yeah, here's U, V, cross V. Okay. Lost my cap. Where did the cap go? Oh well. Ugh. But we actually already have that somewhat. And let me see if I can show you why it is we already have that, why this isn't like ad hoc. Consider, for example, what is I cross J? What direction should that point in? And combined with some algebraic properties of the cross product, which are going to be really the practical exercises for the day, your praxis, this is going to be determined by something. So let's look at what this would be, right? This is 1, 0, 0 cross 0, 1, 0. And so sort of take it from the definition, right? We look at this one times this one plus, or so that's 0 times 0. Should I color coordinate these? Maybe I should. I'll just try to point it out, right? We're talking about y1, z2, that's 0. minus z1, y2, but that's also 0. So we get 0 in the first component. All right, I'll write it out at least this much. 0 times 0 minus 0 times 1. And then middle component, right, we cover that up. And we're going to do z times 1, 0 times 1, minus, and then 0 times, 0 times 0, and then 1 times 0. And then we have, covering this up, I have 1 times 1 minus 0 times 0. And we see that this is just 0, 0, 1. And we have a name for that. That's k hat. So again, right, we take the cross of j and I and j, and we wind up with k hat. So that tells us, right, if our coordinate system is right-handed, then the cross product is right-handed. Okay. So I'm going to erase this one. But I'll just record the conclusion over here. This is because of the way that the cross product acts on the basis vectors of our coordinate system. So now I'm going to talk a little bit about determinants. I'll try to move quickly through that because we're going to talk more about them later. You'll even talk about them much more in other courses that have to do with matrices and matrix theory. And it's really just a mnemonic. It's just a way of memorizing the cross product formula. So I'll try to see if I can't make this a little briefer, right? So if I have a 2 by 2 matrix, so a matrix is just a set of values which we arrange in rows and columns. And we say that the number of rows is 2, the number of columns is 2, and so this is a 2 by 2 matrix. If we want to write the determinant of this matrix, then that's going to be written with abs-val symbols. Sometimes they put those outside of the matrix, but since I'm going to use abs-val of the determinant, I'll just use abs-val to be the actual walls of the matrix instead of a brace, right? So I'll say the determinant of A, B, C, D, like this. And then that's going to be AD minus BC. Some of you might already notice how similar this is to the thing we did in the cross product, right? If these are lists, then I'm taking the first thing times the second thing minus the second thing times the first thing. Okay, so maybe it's not going to be surprising that this is going to give us some way of talking about the cross product in a succinct way. If we have a 3 by 3 matrix, and the determinant really is only something you talk about with square matrices, where you have the same number of rows as columns. That's important, but again, more later. Right, let's say I have A1, A2, A3 is one row, B1, B2, B3 is another row, and C1, C2, C3 is a third row. Then one formula. Now, you probably know many formulas for the determinant. And if you like the, slanted diagonals minus the backward slanted diagonals, fine. But the one that's going to be most useful here is called Laplace's expansion, or the expansion by minors of the determinant. And what you do is you take one of the top row values, A1, and you multiply it by a determinant if you then covered up the row and column that pertain to that. So if we did A1, we'd get rid of the first row, first column, and now we have a submatrix, a 2 by 2 matrix, and we would look at its determinant. And again, you probably notice, hey, now I have nothing that has to do with what was in the first column, in the same way that my cross product doesn't have anything to do with x in the calculation for the x component. Then there's an alternating sequence of pluses and minuses. That's part of the determinant formula. And alternation is, in fact, really the substance of the determinant. Put a pin in that. So we cover up A2 and its column here, and we have B1, B3, C1, C3. And then we flip back to summing. And this is going to be B1, C2, or B1, B2, C1, C2. But then what are these 2 by 2 determinants? We have A1 times B2, C3 minus B3, C2 minus A2 times B1, C3 minus B3, C1 plus A3 times, running out of room, B1, C3 minus B2, C1. Okay, so again, just expanding out these minors. So how can we write, if we have, again, U as x1, y1, z1, and we have V as x2, y2, z2, then how can we write U cross V just succinctly? Well, we remind ourselves this is the determinant of the matrix with the following components. Now, yes, these are mixtures of vectors and numbers as the components of the matrix. Again, this is just a mnemonic. This is just a device to help you remember the formula. We put ijk up top. We took x1, x2, x3 in this row. And we take, y, x, y, z, x1, y1, z1 in this row, and then x2, y2, z2 in this row. And I'll let you compare and contrast, right? If you take the I times minus it, you're going to expand this out to be the cross product formula. Okay, we're almost there. There's only a couple more things that I want to say. One is about another geometric property of the cross product, which is that it does pertain to an area. So if I have, for example, V like this, U some other vector like this, then they naturally make a parallelogram, right? If I, sort of go towards their sum, U plus V, off in this upper corner, there's sort of a natural shape that gets made, right? And we might ask what the area is of that shape. Now, as some of you might remember, that's related to the angle theta, the angle between them. So the area, if I want to just call that A of this parallelogram, is going to be equal to the base times the height. Okay, well, the base is easy. The base is the length of U. But what's the height? Well, let's just look at a little bit of trig. Right, that's the magnitude of V times the sine. It's the opposite of this. Height is dropping a perpendicular, right? So this is times sine, because we're opposite of theta. Move my A over. And so what do we get here? We get V magnitude times sine of theta. Oh, this is exactly the magnitude of the cross product. So the magnitude of the cross product is the area of the parallelogram formed by the two of them. And that should be, so a couple things we could notice there, right? If you had them parallel or anti-parallel, the parallelogram collapses, and you wind up with 0 for an area. On the other hand, if you have an angle of 90 degrees or 270 degrees or some, multiple of, pi over 2, odd multiple of pi over 2, then you would wind up with a rectangle, and it would just be the product. Sine would be 1, and you would just have the product of their two magnitudes. Okay, that's all I wanted to mention about that. Let's look at an example involving the cross product. It's good to get our hands on some actual numbers here. So let's find the cross product and area of the parallelogram formed in the plane by, our vectors from the first example, 3, 2, 1, and 1, 2, 3. Okay? So we'd carry out the calculation, U cross V, just by definition, right? That's a vector. Its first one is 2 times 3 minus 1 times 2. Its second one is 1 times 1 minus 3 times 3. Its third one is 3 times 2 minus 2 times 1. And, simplifying, we would have 4, right? 6 minus 2, that's 4. And then 1 minus 9, that's minus 8. And 6 minus 4, again, that's another 4. So if you like, that's 4i minus 8j plus 4k. Here's component form, here's basis vector form. And then if we want to know the magnitude of this, right, we could say, well, that's U cross V. First of all, there's 2 easy ways to calculate it, right? One of them is to just take the magnitude of this vector that we've got. That's 4 squared plus minus 8 squared plus 4 squared. And 16 plus 16 plus 64, that's the square root of 96, which simplifies to, let's see, well, it's almost 25. It's almost 100. That would be great. But no, we could divide out 8 from this. No, 16 from this. And that would be 16 times 6. So the square root of 16 is 4. And this is 4 square roots of 6. Okay, yes, that's true. We could also use the definition of the area that we got with the sine formula. And we calculated these guys already. These were 14s times sine of cosine inverse of theta, right? We just plug that right up. No. And don't put the 44 approximated in there either. This is no good, right? It's fine, right, if you want a decimal answer. I get that. But you're going to also be able to get an exact answer. And generally, that is what your programs are looking for. I get that some of them don't. I get that some of them are looking for the decimal. Please. There's a way to do this easily, right? What is sine of this cosine of theta? Well, remember that theta was inverse cosine of 5/7. So just draw a quick triangle. What would you have? Well, you would have 5 for the adjacent, right? And 7 for the hypotenuse. That's the ratio 5/7 that you'd be taking in order to get this theta. but then you know what the other angle is, right? It's going to be the square root of 49 minus 25, aka the square root of 24, which is just going to be, 2 radical 6. And so what is sine of theta? Sine of theta is 2 radical 6 over 7. And then that's 4 radical 6 again. Right? So that's also, I think, a better way of still getting the exact radical answer. Would this give you the radical? Absolutely not. Wolfram Alpha or your Chat's GPT would just give you some, decimal approximation of this. Here we have truly what it is with infinite precision in terms of radicals. Meh. All you had to do was draw a triangle. Come on. Okay, so what's the last bit I want to talk about today? The last bit is a last kind of product. I won't say much about it. I'll let it be a little bit more mysterious. But we're going to look at one more kind of scalar product. This that takes in 3 vectors. Okay. So if I have, try to color code. If I have u equal to x1, y1, z1, and I have v equal to x2, y2, z2, and I have w, and I have w equal to x3, y3, z3, then we define the scalar triple product sometimes just called the triple product, is defined as follows. You take v double. It doesn't really get its own symbol usually, but it's the following sequence of things. You dot w with the cross product of u and v. And that's our fella. That's our guy. And of course, you could work that out component-wise, but there's a nice determinant formula way of keeping that intact, which is that the magnitude of this number, and keep in mind, since we're talking about a number, I'm just going to use abs vals to indicate the magnitude of the number. Right? This dot producting a vector with a vector gives you a number. That's the scalar in scalar triple product, and its magnitude, because it could be positive or negative, but for the purposes of what I want to show you, this is just going to be positive. Well, all right. First of all, if you don't want it positive, if you're fine with positive and negative numbers here, you can just do the following. This is just, we'll put the top one along the top, and then we put the other one underneath it. So it's very similar to y2, y1, c1, very similar to the cross product determinant formula, except instead of the unit vectors, the unit basis vectors, you have the components of w. So this one times this one minus this one times this one minus this one times this one minus this one. And why should you care about such a thing? Well, the main idea is that if they're not all coplanar, meaning they don't all lie in the same plane, then what you're going to get from these 3 vectors is sort of a 3-dimensional shape that they span. Right? We follow this one. that. And, sort of following any route that we could take to get to their sum, I would get this sort of skewed parallelogram shape, which we call a parallelepiped. A parallelepiped? I don't remember if that's an O or an A. And it has a volume. And the volume of this parallelepiped, the volume of the shape that these are created by, is going to be, or that is created by these three vectors, is going to be equal to the magnitude of this thing. So I'll just write this as the magnitude. I made them bigger so you don't think that's a magnitude of a vector. It's the absolute value of the determinant of this matrix. And if you do that, you get the volume of this thing. And what's cool is that this volume is equal to 0 if and only if V, W, and U are not coplanar. And what's great about if and only ifs is that you can negate both sides and it's still valid. So for example, V is non-zero, you have a non-zero volume if, oh, I'm sorry, I've said this wrong. It isn't 0, it has a non-zero volume if they're not coplanar. If you get that this volume is 0, then W, V, and U are coplanar. Provided you haven't, you don't have a 0 vector lurking in here. If one of these is the 0 vector, then a whole row of this matrix is 0, and its determinant will wind up being 0. But if you have non-zero vectors, then they may be coplanar or they may not be. If they are coplanar and they all lie on the same plane, this squishes the parallelepiped's volume to 0, and that means your scalar product is 0. So now you have a test that you could perform on any three vectors and say, well, are they coplanar or not? Right? If you take the scalar triple product and it's 0, they're coplanar, as long as they weren't 0 to start with. And if they're not, if the scalar triple product is not 0, they're not coplanar. And that means that they span a three-dimensional space. You could write any single point or vector in the plane as a linear combination of that U, W, and V. Okay, that's all that I will say for now about these things. Let me give you some homework. So I have two problems for homework, or praxis, that I'd like you to try on your own at home. So number one, prove the following. These are not hard proofs. These are just going to be basically writing down things in terms of their definitions, right? And making sure that one side equals the other side. That's all I mean by a proof in this case. I'm not asking for induction. I'm not asking for anything really complicated. I'm just asking for you to make sure that one side equals the other side in the following formula. So here's some algebraic properties of the cross product. Number one, it is antisymmetric. This has to do with the odd nature of cosine, right? It's an odd function. Number two, it's distributive. Right? So you can distribute it around sums of vectors. Number three, you can distribute scalars however you like. It's associative with reference to scalars. So either you could scale the cross product, you could scale one of them and then cross product, or you could scale the other one and then cross product, and it would be the same. Number 4. If you take the 0 vector and you cross product with anything, doesn't matter how you do it, left or right, you get the 0 vector in this case. That's an easy one to show. Number 5, any vector cross product with itself is 0 as a vector. Well, think about it. What's the angle between them? Number 6, if I take the dot product, this is the scalar triple product. If I take the scalar triple product, I can permute the things as long as I sort of keep the order correct. So I could move this to the front and dot that instead, and then this would be U cross V. Remember, order matters. Order matters with the cross product, so the order changing here is going to matter. This is a W. There we go. And then likewise, of course, you'd have V dotted with W cross U. Okay, so these are some algebraic properties. What about geometric properties? These we already talked about in the lecture, but some of them I didn't prove. You may want to prove them yourself. Number 1. So U cross V is orthogonal to U and V. Number 2, that, and this one we proved already, that the cross product is equal to, its magnitude is equal to the magnitudes product times the sine of the angle between them. Number 4, that the magnitude is equal to the area of the parallelogram formed by with sides U and V. We sort of already proved that one as well. So if you, wait, I've skipped one. Oh, oops. So let's call that 3. And let's call 4 that U cross V is equal to 0 if and only if U is a scalar multiple of V. That means they lie on the same line. So C, some real number. Can I scale V to get U? Do they lie in the same one-dimensional subspace? If so, yeah, then their cross product is going to be 0, right? Again, think about the angle between them. So that's one part of homework. I consider that one to be super duper easy. If you just write down the definitions on both sides, you'll see, and by the definitions, right, I mean their formula on both sides, you'll see that both sides are equal, and that constitutes the proof. This second one is a bit harder of a proof, but still, I'll give you some hints. And if you get stuck, send me an email. So if U is not a constant multiple of V, and they're not the 0 vector, neither of them, then for every x and y in R, right, for every 2 numbers, x and y, there are 2 unique numbers such that, let's call them, let's give them a name. let's say two unique numbers a and b, who are also real numbers, such that a times u plus b times v is equal to the vector xy. Right? I said that if they aren't scalar multiples of each other, then they sort of span a plane. And so, in other words, we should be able, for every point on that plane, to multiply them by something, right? Maybe multiply by a negative in this case, and maybe scale by a little bit more than v in this case, and get to that number, right? There should be some way to do it. And I will say, let's let this be in the plane, right? Let's not worry about 3 dimensions. Let's just worry about this vector in the plane. We'll say u and v are, in the vector space R2, right? That these are 2-dimensional vectors. So I'll give you a hint. Write their components, right? U is equal to x1, y1. Write v is equal to x2, y2. And then what does this equation mean in terms of the components? Well, it means 2 equations, right? It means that a times x1, if you distribute a in here, plus b times x2 has got to be equal to this number x, and you have a times y1 plus b times y2 is equal to this number y. Now remember, a and b are your unknowns. Can you solve this equation? Yes? No? Maybe? Sometimes? Sometimes? I don't know. Okay, so that's your homework. That's your praxis. Good luck. May the force be with you, and have a great day.